Everybody, it's Mrs. Harbin, and we're doing video notes 2-1. We got to do this: valence electrons, SPD and F, electron configurations, and the rules. So here we go. Make sure you read Chapter 5, Section 5.1, starting at page 130 to 132, and Section 5.2. Read all those pages, please, and look at them. All right. That's a smart little rat there, or mouse. Okay, so first question is, where are the electrons? So we talked about the nucleus, we know where the protons are, and we know there are some energy levels, but where are the electrons for real? Well, there are 4 major energy levels that get used, well, 4 to 6 major energy levels that get used by the electrons because they have to go somewhere, all right? So the number of the energy levels is called N, and there are principal energy levels. Each energy level has places to put electrons. The first energy level has 1 place to put electrons. We call those sublevels. Sublevels, all right? And then the second energy level has 2 sublevels. 1, 2. Third energy level has 1, 2, 3 sublevels. They're called SP, D, and F. So the fourth energy level has 4 sublevels, all right? Any guesses as to how many sublevels the fifth energy level would have? If you said 5, you're right. Okay. Then each sublevel has orbitals. An S sublevel has 1 orbital. A P sublevel has 3 orbitals. So 1, 2, 3 orbitals. A D sublevel has 5 orbitals, and an F sublevel has 7 orbitals. Okay, so then how many how many total orbitals are in an energy level? Well, the number of orbitals in each sublevel, and then the maximum number of electrons, you can put 2 into each sublevel. So fourth energy level can hold 32 electrons, third can hold 18, second can hold 8, and the first energy level can hold 2. Now, you could think of it like rings, even though we know rings are wrong. But here we got the tiny nucleus, and then around the tiny nucleus is the first energy level. The first energy level only has 1 sublevel, and because it's small and close to the nucleus, so that's why. So it's really close there. Then you can go out to the second energy level. Second energy level has 2 sublevels, S and P, and there's actually 3 orbitals in the P sublevel. Okay. Then you can go to the third energy level, and the third energy level has an S, a P, and a D sublevel. And then the P spreads out into 3, the D spreads out into 5, and that's the third energy level. Fourth energy level would be even further away from the nucleus. Okay. So where are the electrons? Electrons are in energy levels. Where in energy level? Energy levels in the sublevels. Where in the sublevels? In the orbitals. So how do we explain where the electrons are in atoms? Okay. So this is the nucleus right there. See that first blue sphere? That's the first energy level, and that's its sublevel, the s orbital. Then you go to the second energy level, and you get an s orbital in the second energy level. Same shape, just bigger. Then in the second energy level, you could have the p sublevel, and there are actually 3 orbitals in the p sublevel. So they're in 3 different directions along the nucleus, x, y, and z axis. Then you go to the third energy level. Look, it's a sphere, okay, for the s orbital. And then there'd be p orbitals in the third energy level. And then in the third energy level, you'll get these d orbitals. Then finally, you'd have the fourth energy level, which has the S, the P, the D, and the F sublevels. Okay, so how can you describe where the electrons are? Well, electrons will put these rules in, fill lowest energy sublevels first. That's called the Aufbau principle. That means it builds up. Electrons build up from lowest energy. Who can spell here? Principle. Okay, from lowest energy to highest energy level. Next, only 2 electrons per orbital, and they have to have opposite spin. That's Pauli exclusion principle. Exclusion principle. All right. And then the third rule that you have to follow, or that gets followed when you describe electrons, is to put 1 electron per sublevel until they are half filled before you double up. And that's called Hund's rule. Hund's rule. So 3 rules that you got to go by. So what does that mean? Well, we can do what are called orbital diagrams to represent electrons. So you can do circles or you can do boxes. You can do a circle or a box. Now, the lowest energy level is the 1s orbital. So then, if an element has this many electrons, 2 of them go in the 1s orbital, then 2 go in the 2s, and then 1, 2, 3, 4, 5, 6 go into the 2p sublevel. And then the 3s orbital has 2, and then 6 in the 3p level, and then 1 in the 4s sublevel. So let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. 19 electrons. Which element has 19 electrons? Well, the one that has 19 protons. So it's potassium. So this is the orbital diagram for potassium. How do I know? Well, I counted the electrons, and we're assuming it's neutral. Okay, so that means if it has 19 electrons, it also has 19 electrons in the nucleus. So this is what you would use to show every element, and you would just fill up these energy levels using the rules that we just practice, and we'll keep practicing. Okay, so here's what's called an orbital diagram for sulfur. Instead of writing it up the page, it just goes across, but it's the same thing. How do I know it's sulfur? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is sulfur. Sulfur's got 16 protons, so in a sulfur atom, there are 16 electrons, and this would be the orbital diagram. Why are these two not put together? Because Hund's rule says you got to fill them one at a time until you have to double up. Since we have 4 in there, then you can only put 3 across, and then you have to double up. Okay, how do we write an electron configuration? Well, you can start with an orbital diagram and translate it into what's called an electron configuration. So you would say, okay, this is 1, 2, this is sulfur again. So sulfur, and then I have the 1s orbital is holding 2 electrons. 2s orbital is holding 2. The 2p orbital is holding 6 electrons. The 3s orbital is holding 2, and the 3p orbital is holding 4 electrons. So how do you know it's right? Well, count those electrons. Make sure an s orbital only has one shape, so it can only hold 2. Another s orbital only has one shape, but the p orbital has 3 different lobes. So there's 3 boxes to put electrons in the p sublevel. Okay, so remember to fill them up before you move up and go on. So this is an electron configuration. Electron configuration. How is it different? Well, it's a kind of shorthand for the orbital diagram. This is an orbital diagram. Okay, electron configuration, orbital orbital diagram. All right, how do you fill them? Well, you can go back and memorize this, or you can use this little trick. So look, I put all the s orbitals first, and then I put the p orbitals starting with 2, second energy level, because that's where it starts, then the d orbitals, then the f orbitals. And then to fill them up, you start over here and you say, okay, fill up the 1s first, then the 2s, then the 2p, then the 3s, and you come back down, draw your arrow diagonal, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, etc. So you start at the first one, put your arrow up, and then go to the bottom of the next arrow and go up. You should be able to draw that, and then you'll know how to fill them. Okay, so let's practice. Let's do sodium. Sodium, how do I know how many electrons? Sodium has 11 protons, so guess what? It's going to have 11 electrons when it's neutral. So it says here 1s. All right, how many can fit in s orbital? 2, so I got to move on. So I start here and I go, oh, 2s. S orbitals can hold 2. All right, then 2p. 2p can hold up to 6. That's 10, so I have to go to 3s, and that can hold 1. So that's 11 electrons. If I add up those top numbers, they look like exponents, but that's representing the number of electrons. Okay, electron configuration for sodium ion. Well, I'm going to tell you that a sodium ion has a +1 charge. By the end of this unit, we'll be able to do it. So +1 charge means 1 electron is gone. So there are 11 protons always. If there's only 10 electrons, we would do this 1s2, 2s2, 2p6, and then we're done because it's sodium with 11 protons, but then it says a +1 charge, there's 1 less electron, so only 10 electrons. Okay, atoms are neutral, so this number equals the number of electrons. Ions have charge. If it's a +1 charge, then this many protons, but 1 less electron. All right, you can also use the periodic table. So this filling diagram, you can follow using the periodic table, because the first thing across on the periodic table are 2 boxes, hydrogen and helium, and that represents the 1s orbital, then it's full. Then you can go to the second row on the periodic table. Over here are 2 boxes for the 2s1 and the 2s2, but then that's full. Jump over to here, we're still in the second row, but it's called the p block, and it goes 1 to 6, so that's 6 electrons. And then that would take us to 10 total electrons, and then we go to the third energy level over here, it's the s orbital. Look at that. If you follow this, it follows this. Okay, so that, oh, hey, we don't need that. Okay, so then, okay, so over here, after 3s, you go down here, and then it's 3p, and that can hold up to 6, so we take care of 18 electrons by here. Then we go to the fourth row on the periodic table. over here is S, over here is S. Right? What's next? Oh, look, 3D. What? This is a fourth row. Yeah, but this is the third energy level d orbitals. We didn't talk about how many d can hold. D can hold up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Coincidence? No. Totally what we're talking about here. So then 3D can hold up to 10. And after 3D, we come back to the fourth. We're still in the fourth row. And you go here, and then we get up to 36 electrons by the time we get to there. Okay? And we could keep going. 5, 5s, 4d, 5p. And by that time, we've taken care of 54 total electrons. Okay? Now, down here, we go to here, and then back up. Down here, we go to here, and then back up. Okay? So, there's a little overlap in the energy levels, so 3d actually fills after 4s. Is there a shorter way to do this? Yes. There's called the noble gas electron configuration. So here's what you do. 1, you find the noble gas that comes before the element of interest, and then you continue from there. So let's try barium. Barium is right here. That's our element of interest. What noble gas? So noble gases are in this column. What noble gas comes before barium? Well, it's xenon. Okay. So we'd start by saying, all right, barium has 56 protons. It's an atom, has 56 electrons. I'm going to put the element Xe in brackets for xenon. Okay, that takes care of, well, 54 electrons. So now I'm coming down to this row right here, which is 1, 2, 3, 4, 5, 6th row. So I'm at 6. If I go back to here, I'm like, oh, over here, it's going to be 6s. So I'm going to say 6s2, and that takes care of 54, 55, 56 electrons. It's called the noble gas electron configuration. It's shorter, and it's cool. You got to be able to do both. All right, so keep writing. There's a little more to go. What about these electrons is most important? Electron configurations help us figure out the valence electrons for elements, okay? And so I want you to know that valence electrons are outermost electrons. It's a periodic trend, okay? These atoms have 1 valence electron. These atoms have 2 valence electrons. These atoms have 3 valence electrons, 4, 5, 6, 7, and starting here, 8 valence electrons. Helium only has 2 valence electrons. So the number of valence electrons is going to help us decide how elements bond. Okay, valence electrons help us determine charge too. So for instance, lithium has 1 valence electron. So then it usually loses that one, and then it's more like helium, and all these things over here are stable. We'll learn about them. So they're stable. Okay. Potassium has 1 valence electron. All right, it ends in 1, 2, 3, 4. Potassium ends in 4s1. So it has 1 outer electron. So when it loses that 1 outer electron, it becomes a lot more like argon, which is more stable, and then it has 8 outer electrons, but in its lower shell. Okay, oxygen. Oxygen has 6 valence electrons. How do I know? 1, 2, 3, 4, 5, 6. Okay, so then what does oxygen want to do? Oxygen wants to gain 1, 2 valence electrons, so it's more like neon. Okay, oxygen would end in 1s2, 2s2, 2p4. 1s2, 2s2, 2p, 1, 2, 3, 4. So what does oxygen want to do? It wants to get 2 more electrons to be 1s2, 2s2, 2p6, and that is a full set of valence electrons. 8 is great. So here are the valence ones, just the outer highest energy level S and P electrons. Okay, let's play. What element am I? Dun, dun, dun. So let's see. 2, 4, 10, 11, 12, 18, 19 valence electrons. Okay, 19 valence electrons, 19 protons. It's potassium. Is that what you guessed? Try this one. 20 valence electrons. What are you thinking? Are you thinking calcium? Because that's what it is. 20 electrons. Count the superscripts. All right. How about what ion am I? All right. So I start out like this. 7 valence. I mean, not 7. Well, 7 valence electrons, but 7, 8, 9 total electrons. What element has 9 total electrons? Fluorine. Plus 1 more electron gives 8 outer electrons, but 10 total. So it becomes fluoride because it's 9 to start with, gains an extra one. This ion is fluoride with a -1 charge. Okay, make sure to read chapter 5 of the book. I want you now to answer these 2 questions. Okay, look at table 1, explain why 32 electrons can fit into the 4th energy level. Look at table 5.3 explain how the orbital filling diagram for nitrogen. So in that table, see a lot of elements. Look for nitrogen. How it shows Hund's rule. And then you answered those. And here's your review, okay? So here's what I want you to remember. Electron configurations show a periodic pattern, and that's what this unit's about, okay? Use your 3 rules. There are 3 rules to fill up the electron configurations in the orbitals, okay? Valence electrons are outermost S and P electrons. Valence electrons are used for bonding, and hopefully you can tell what valence electrons are. Compare S, P, D, and F orbitals, all right? You can use these 3 rules to do orbital diagrams and electron configurations, short form and long form, okay? Atoms and ions. You can identify elements based on their electron configurations. Oh, I think you might have a good feeling about this, guys. All right, we'll practice in class. Thanks for playing. Peace out. Harbs.